Welcome to the Mcat Basics podcast, brought to you by the physicians at Med School Coach. Each week, Sam Smith breaks down high-yield Mcat topics so you can score as high as possible on test day.
Hello, I am Sam Smith, and this is Sam's Mcat Basics. This podcast covers the most important topics put out on the AAMC Mcat each year, and I determined this list by going through all the official practice materials that the AAMC puts out, and also some third-party practice material, and just put together this big list of topics that consistently kept on showing up, and ranked those topics and made podcasts out of it. This podcast covers types of studies in research design. I'm going to go over the different types of variables that you'll see in studies, as well as some terms you'll see on the Mcat that are relating to study design. This will include things like the 6 different types of validity and confounding variables. And then I'll go on and I'll start talking about the different kinds of studies. And this is going to be things like observational studies, cross-sectional studies, cohort studies, experimental, etc. And then lastly, I'm going to touch on study limitations and bias. In my opinion, that's a very big part of the Mcat. They love to ask questions about, what are the limitations of this study? Where did this researcher have bias? What was this bias called? So that's huge. And this material will show up on 3 out of the 4 Mcat sections. This will include chemical and physical foundations of biological systems, biological and biochemical foundations of living systems, and lastly, psychological, social, and biological foundations of behavior. And it will mostly show up on that psych-soc part, so just keep note of that. So the first thing I want to talk about are study variables. The most important variables to know here are the independent variable and the dependent variable. And I'm sure this has been drilled into you since the first grade, but I'm just going to go over them real quick here. So the independent variable is a variable that the experimenter is manipulating in the experiment. And the dependent variable, on the other hand, is the variable that is being measured by the experimenter. So let's take an example in which an experimenter is trying to discover how plant height varies with exposure to sun. So what they hypothesize is that with more sunlight, these plants will grow taller. So in this case, think about it real fast. The independent variable is the variable that the experimenter is changing. And so in this case, that is the amount of time in which these plants are exposed to sunlight. And what the experimenter is measuring, which is the dependent variable, is plant height. Another variable you're likely to see in relation to studies is called a correlation variable, and this is a statistical variable that shows how related 2 variables are. And so the variable that you'll see is called the Pearson correlation coefficient, and this is on a scale of 1 to -1. So if 2 variables are perfectly positively correlated, i.e., as one increases, the other increases, then they will have a Pearson correlation coefficient of 1. On the other hand, if they have a perfectly negative correlation, that means, as one increases, one decreases, then they will have a correlation coefficient of -1. If they are correlated, but it's not a perfectly or a very strong correlation, you might have something between 1 and 0 or between 0 and -1. You might be thinking, okay, what about when the correlation coefficient is equal to 0? So if you have a correlation coefficient of 0, then you can say that these 2 variables that you're looking at are not correlated. I recently got off a flight less than 24 hours ago, and so the example I'm going to give here is the relationship between the number of crying babies on a plane and your annoyance on a plane. So for most people, this is probably a Pearson correlation coefficient of 1. The more crying babies, the more annoyed you get, right? And it's a perfect correlation. However, there might be some people in which there's a correlation coefficient of -1. In other words, the more crying babies you have on a plane, the less annoyed they get and the more happy they get. Not to delve too far into psychology here, but those kind of people are what we call psychopaths. And then, you might have the understanding mothers or understanding fathers who are like, I've been there. It sucks for them. And, maybe the crying babies doesn't even affect them. Maybe you're a dad who's had 5 kids and, has lived their whole life with crying babies. And so they just shrug it off. They're like, yeah, who cares? It doesn't affect me. And that would be a Pearson correlation coefficient of 0, right? Those two variables wouldn't even be related for these understanding mothers and fathers. And another variable that is related to correlation but very distinctly different is causation. So you'll say that these two variables have a causal relationship. And in this case, that means that one variable causes another. For whatever reason, I always read the word causal as casual. It's spelled the same. So anyways, it's important to note that causation and correlation are often confused. So just because two variables are correlated together, i.e., let's say they have a Pearson correlation coefficient of 1, that doesn't necessarily mean that these variables cause each other, or it doesn't mean that one variable causes the other. Let's take a classic example here. So say you look at the correlation between sunglasses and ice cream sales at a local grocery store. And the statistician who is doing this work comes up with a Pearson correlation coefficient of 0.82. It's a pretty strong correlation there. If you were to assume that this was a causal relationship, you would say that the sunglasses sales are directly causing more ice cream sales. However, this is obviously not true, right? Just because you're wearing sunglasses doesn't mean you're going to eat more ice cream, I would hope. What's going on here is there's another variable that's causing both of these. So you look back and you say, okay, what's causing both of these? Well, in a lot of cases, a warm, sunny day is going to cause you to wear wear sunglasses and eat ice cream. So really keep that in mind, because I think sometimes the MCAT will try to throw that in some of the answer choices, is say X causes Y, even though they've told you that these variables are correlated in some manner. They've said these variables are correlated, and at that point when they say X causes Y in the answer, okay, that's a wrong answer. I'm going to cross that one out. It helps you in terms of process of elimination. The last variable I want to talk about here is a variable called the confounding variable. And the confounding variable is a variable that influences both the dependent variable and the independent variable, causing a spurious association. So a confounder is basically just some variable that isn't accounted for in your experiment and therefore plays a role in whatever effect is measured by a scientist. And so a good example here is the example of risk of Down syndrome and higher parity. And in this case, parity is just the mother's number of pregnancies. So if you look at the historical data, you'll see that mothers that have more children or more pregnancies tend to have higher risks of Down syndrome. And so it's easy to look at that data and say, okay, well, obviously getting pregnant more times must have some causal effect on your pregnancies resulting in a baby that has Down syndrome. However, there's a variable here that's a confounding variable that isn't accounted for. And what is that? Well, in this case, it's that mothers who have more pregnancies tend to be older, obviously, right? The more pregnancies you have, the older you're going to be. So the confounding variable in this case is age, right? So that affects the number of pregnancies that a woman has had, and that also directly affects the risk of Down syndrome, right? That's what we know is the risk factor in this case, higher age. So again, a confounder is a variable that influences both the independent and dependent variable and causes some spurious association between variables that is not true. The next variable or term I want to go over is called the odds ratio. The odds ratio represents the odds that an outcome will occur given a particular exposure compared to the odds of the outcome occurring in the absence of that exposure. And so these odds ratios are commonly used in case-controlled studies as well as cross-sectional and cohort studies. However, most commonly in most commonly in case control. And so when you have a odds ratio equal to 1, that essentially means that the exposure does not affect the odds of some outcome. However, if you have an odds ratio greater than 1, then you know that the exposure is associated with higher odds of the outcome that you're measuring. And then on the flip side, if the odds ratio is less than 1, then you can say the exposure is associated with lower odds of whatever outcome you're measuring. So here's a quick example just to kind of help you grasp what an odds ratio is. So currently the odds ratio for lung cancer in smokers relative to non-smokers is 40.4. So essentially that's saying that if you smoke, you are 40 times more likely to develop lung cancer, which obviously this is a huge number. It's important to note, though, that for odds ratio, this is a continuous number. This is not like the Pearson correlation coefficient where you can either have 1 or -1, right? This is a continuous number and it isn't restricted by any bounds. Another example is, you had a study done on a group of people in Thailand that looked at consumption of sugar-sweetened beverages and type 2 diabetes incidence in Thai adults. And so the results from this 8-year prospective study showed that exposure to sweetened beverages increases the likelihood of developing diabetes by about 2. So, it's not 40 like in the case of smoking, which is just a massive odds ratio, but it still is saying that, this likely has some effect on diabetes.
In general, the thing I always try to say to our students, and certainly prospective students, people desire the product coming out of the DO schools. And we hear very, very positive feedback from program directors and institutions that for a long time have been accepting DO students. And certainly the stories about them becoming leaders and practitioners in those institutions.
That was a clip from the Prospective Doctor podcast with the CEO and president of the American Association of Colleges of Osteopathic Medicine, or AACOM. The Prospective Doctor podcast is great. It features weekly interviews with interesting doctors and different figures in medicine. If you're a pre-med or medical student, I highly recommend it, and I really do listen every week, and I feel like I'm learning something new and valuable with each episode. So if you're looking for a new podcast, go search Prospective Doctor Podcast in your podcasting app and take a listen. All right, now that I've covered odds ratio, I'm going to go into validity. So validity refers to a test's or experiment's ability to measure what it's supposed to measure. And there are two different kind of categories of validity I'm going to talk about. I'm going to talk about experimental validity and test validity. So in the case of experimental validity, this is looking at how the results of some experiment, it looks at the results of some experiment, whereas test validity looks at the validity of, you guessed it, a test. So in terms of experimental validity, there are two main types, internal validity and external validity. So internal validity basically asks whether the effects observed in the study are due to the manipulation of the independent variable. And so this is basically saying, okay, is your experiment a good experiment? And so this is why you run your experiment with controls, and you make sure that you don't have any confounding variables that are affecting what you're trying to measure. And so then you have external validity, and external validity refers to the extent to which the study can be generalized to another setting, which is called ecological validity, to other people, which is called population validity, or to another period of time, which is historical validity. And so a quick example of this is when we take an animal study, say we're trying to test some new kind of drug, and first we test that drug on mice, right? And that's because we can then extrapolate that data to humans. So this is a type of populational validity. Is your study valid from mice, and can we extrapolate that then to humans? So again, internal validity refers to how good your experiment is. External validity, how well does your experiment apply to other situations? So for test validity, there's a few different types I'm going to talk about. And so in this case, a test is something like a questionnaire, an IQ test, etc. And so there's two kind of main types of test validity. There's criterion validity, which measures how well one measure predicts an outcome for another measure. And then we also have content validity, which is how legitimate is the test at measuring what it claims to measure, i.e., are you asking the right questions in order to be able to draw conclusions? So in terms of criterion validity, we have concurrent validity, which asks, does the test measure relate to an existing measure? So let's give an example of an IQ test. Say researchers are inventing some new IQ test, and then they'll take that new IQ test and ask, okay, how do people score compared to the normal original IQ test? And if those scores are very similar, then you'll say that your new test has concurrent validity. Another type of criterion validity is predictive validity. So this asks, does the test predict performance on a related criteria? i.e., is your test good at predicting? So, you say you take again your new IQ test. Now you look at some other measure of intelligence and you say, how well does this correlate? How well does this predict how this individual is going to score on some other intelligence test? So let's talk now about content validity. Again, content validity is how legitimate is the test at measuring what it says it's measuring. So in terms of content validity, we have construct validity, which is, which asks, does this test relate to the underlying theoretical concepts? So for your new IQ test, you'd say, okay, does this new test actually test intelligence? Does this relate to the theoretical concepts behind intelligence? Well, this as of now is kind of debated within different branches of science. Obviously, I'm sure you've heard people say, "Oh, IQ test doesn't actually test intelligence. That thing sucks." And some people are very big proponents of the IQ test. But just understand that construct validity asks whether your test relates to the underlying theoretical concepts. And lastly, in content validity, we have face validity. And that basically asks the question, does this look like it'll test what it says it tests? And this is kind of the least sophisticated measure of validity. Imagine yourself just kind of glancing over this new IQ test that you've made and asking, okay, does this look like it would test intelligence? If it was something like, number one, go run 20 miles, and then number two, do 40 push-ups, and obviously you're going to say, okay, this doesn't test intelligence. On its face, it does not look valid. And of course, this is a kind of a superficial measure. But when you're first introduced to some test, this is valuable in determining whether or not, this gives a first look at validity. It can be useful for that. So again, here we have two main types of validity that we're talking about. We're talking about experimental validity and test validity. Overall, I think experimental validity is the most important to know. And again, that breaks down into internal validity and external validity. So know these terms and understand how they can be applied to questions on the MCAT. All right, the last kind of variable I want to talk about here is specificity versus sensitivity. So test sensitivity is the ability of a test to correctly identify those with the disease. So these are called true positives. And on the other hand, you have test specificity, which is the ability of some tests to correctly identify those without the disease, and that's a true negative. And so when I'm talking test here, think about like some kind of diagnostic test. So let's talk about HIV, for instance. So when HIV was first detected back in the 1970s, doctors used an enzyme-linked immunosorbent assay to detect HIV antibodies, also called an ELISA. And these antibodies typically took weeks to show up in the blood after a person got infected with HIV. So essentially, you could be very infected with HIV, have a very high viral load, and not be diagnosed. Why is that? Because it takes, a buffer of a few weeks to develop those antibodies that then show up on the ELISA. So a lot of people, that were infected were not diagnosed and therefore could go on and infect more people. However, nowadays, they use a different method. So this is how it works now. Essentially, they take your blood and primers that are specific for different parts of the HIV viral genome, and very likely they'll use primers that bind to very conserved regions of the HIV genome. Obviously, viruses tend to mutate, so if it mutates and now your primers don't bind to that sequence, then you'd kind of be screwed. So they look for very conserved parts of the viral genome. They make these primers, and then what they do is they amplify these sequences using qPCR. And if you go back to the genetics podcast, you can hear a little bit about qPCR, but essentially that lets you see how much amplification is going on in a PCR over time. So you can watch that kind of live. So they throw all these ingredients in, you got primers, polymerase, probe, and if that they recognize there's, if they see some signal from your blood on this qPCR, they know that, okay, there's viral sequence, you likely have HIV virus that you're producing. And so this test was a lot better in terms of detecting patients when they were infected. So in this case, you want a test that is very sensitive, right? So you want a test that is able to correctly identify people who have the disease. You don't want people that have HIV to be slipping through the cracks. And you also want a test that is also specific, right? You don't want to be giving people a incorrect positive diagnosis for HIV. That would be not good. So it's important that a test is both specific and sensitive, and it's also important you understand the difference between specificity and sensitivity. All right, now that I went over a lot of the research variables and terms, I'm going to get into the types of studies that you're likely to see on the MCAT. All right, so what I'm going to do is I'm going to go through a bunch of different types of studies now, and you're likely going to see these come up on the Psych-Soc section of the MCAT. And what I'll do is I'll give you the definition, then I'll go through some examples that'll kind of help you remember what exactly these tests are, or what types of studies these are. And these are ordered by importance, the way I'm going to present them. So really pay attention to the first 1, 2, 3, 4, 5. So pay attention to the first 5 that I present. The other ones I put on there just because I want you to do extra well on the MCAT. All right, so the first type of study you should know is called an experimental study. And in an experimental study, the investigator artificially manipulates the study factors or variables. And in a lot of cases, this is some kind of therapeutic regimen. And they do this in a very controlled environment. And so in this case, you have an experimental group, you have a control group. The control group does not receive whatever treatment or test variable you have. And then the experimental group receives that tested variable. So here's just a quick example. You have a clinical trial, which you're looking at some kind of new vaccine to be tested. Let's say you have 20 people that enter that trial. You split these people in half. You'll have 10 of them receive this new vaccine, and you'll have 10 of them that will receive some kind of placebo. Let's just say in this case, it's an injection of saline solution. And again, this is the control group. And so that this control kind of essentially accounts for being injected with something and then also having the thoughts that, okay, I just got injected, I will be protected against this disease. So that is an experimental study. On the other hand, you have something called an observational study. And so this draws conclusions from a sample of a population where the independent variable is not under the control of the researcher. In other words, what scientists do in an observational study is they observe some kind of behavior and then they try to draw conclusions from those observations. Unlike experimental studies, they have no control over the participants. So here's a quick example. Say that you have a group of scientists who are interested in happiness and social media usage. So what they do is they interview 50 different adults. They ask them, okay, how many hours a week or hours a day do you spend on social media? and then they give them some kind of survey to quantify their happiness. And through those surveys, they are able to see that people who spend more time on social media tend to be less happy. And this, of course, is a self-diagnosis of being less happy. But as you can see here, the scientists are not manipulating any kind of independent variable. They're simply interviewing people about their habits and lifestyle and then making conclusions from those interviews. However, a big problem with observational studies is that confounding variables may play a role in the trend seen. So again, a confounder is a variable that influences both the independent variable and the dependent variable. So taking the social media study I just talked about, let's say that the experimenters conclude that social media is making people unhappy. Apparently, that's the cause. Let's say they conclude that social media is the cause. Well, what if people that spend more time on social media tend to skip out on exercise or other things in their life that lead to that unhappiness? And again, I'm making this example up, but let's just say that's the case. Well, then you can't conclude that social media itself is causing this unhappiness. There's some other confounding variable that's at play here. Another interesting case where confounding variables play a role is in a 2012 study done by the Harvard School of Public Medicine. They published a study linking red meat consumption to increased risk of total cardiovascular and cancer mortality. The research was joined with a lot of other research that kind of pointed to the same things. And the way the study was done was like this. So what they did is they collected dietary data from participants every 4 years from 1984 to 2006 using a food frequency questionnaire and a biennial follow-up questionnaire that collected lifestyle and medical information like height, weight, medication, smoking, and family history of illnesses. And the food frequency questionnaire asked participants to estimate their usual intake of different types of food from the previous year. And then they used that data to then conclude that the consumption of red meat correlated to increased risk of total cardiovascular and cancer mortality. But what a lot of critics argued in this study was that there are too many confounding variables that were not controlled for. So say here that you are a participant in this study and you're eating a burger and a milkshake every day, right? That's a ton of red meat. You're eating a shit ton of red meat, but you're also eating a lot of processed foods. What about the burger bun? What about a milkshake every day? What about all that sugar? We know that sugar has obviously some negative health effects. And, I obviously have some bias on this case just because I love eating hamburgers and I love eating meat, but you can see that there are a lot of potential variables that were not really looked at in this study that could also affect all-cause mortality and cancer mortality, etc. All right, so now that I talked about what an observational study is, I'm going to go over 3 different types of observational studies. The first is case control, the second is cross-sectional, and the third is cohort. So a case control study, which again is a type of observational study, is a study that compares patients who have a disease or outcome of interest, and those are called the cases, with patients who do not have this disease or outcome, which are called the control, i.e. the name case control. So what this type of study does is it looks back retrospectively to compare how frequently the exposure to a risk factor is present in each of these groups, the case and the control, to determine the relationship between the risk factor and the disease. So let's give an example here of, let's say 100 people are interviewed about their vaping habits, and then they're separated into 2 groups, those who have lung cancer, which are the case group, and those who do not have lung cancer, the control group. Then the incidence of vaping in each group is investigated to answer the question, obviously here, which is, does vaping increase your risk of lung cancer? And what they do is they'll give a questionnaire of some kind and say, okay, how long have you been vaping for? Have you vaped? How many times? Blah, blah, blah. And then they're going to try to link those together. So that's case control. Now let's talk about cross-sectional. So cross-sectional is a type of observational study that analyzes data from a population or a representative subset of a population at a specific point in time. And so that's kind of how I remember what a cross-sectional study is. I'll think you're taking a slice or a cross-section of time and analyzing. So again, let's take the example of vaping and apply a cross-sectional study to it. So let's say scientists interview 100 people in 2002 to assess how vaping relates to gender. They find out that it is dominated by male. Let's say 89% of vapors are male. I'm just making this up, but it is true that there are more male vapors than females. So what the scientists did here is they looked at some certain point in time and they looked at prevalence. And so that's a big thing. That's a big important factor of a cross-sectional study, is that they look for prevalence in a population. So, that might be what's the prevalence in males versus females, which is this example. Or it might be, what's the prevalence in this population in general? What's the prevalence of disease XY in a population in New Guinea? Something like that. So when you see cross-sectional study, think in a study where you're taking a slice at some point in time and you're assessing the prevalence in some population. All right, so the last type of observational study I want to talk about is called a cohort study. So in a cohort study, data is taken from or sampled from a cohort, which is a group of common people who share some defining characteristic, typically those who experience some common event, and that's such as, like a birth. They all born around the same time, which is different generations, or, let's say they graduated from college at the same time. And so in a cohort study, scientists follow this cohort through time, and they perform cross-sectional measurements throughout time. In other words, you have this group of people who share some defining characteristic, and they're followed by scientists throughout time, and at different time intervals, they're, given some kind of questionnaire or something is measured about them, and, scientists try to make some kind of conclusion. And so a lot of times a cohort is defined in terms of people that are being exposed to some event. So let's give an example here in which you have a group of people that, for whatever reason, are all exposed to X-rays, and they're exposed to this massive amount of X-rays. It's a group of 20 people. Let's just say they're chilling in the hospital, and the X-ray machine exploded, and they're all exposed to a massive amount of X-ray radiation. And so these 20 people make up the cohort. And now scientists are interested, okay, what's going to happen to these people throughout their lives? Are they at a higher risk of developing cancer, other diseases? What's going to happen to them? So what happens is, every 5 years, the scientists will take them in for checkups. They'll, check their blood. They might give them MRIs to check for tumors, and they might give them some kind of questionnaires to assess how they are feeling overall, or how their mental health is. So again, that is a cohort study. So again, to summarize these three different kinds of studies, because they are very important for the MCAT, you will see, at least one of these. You'll see some kind of question where it asks you what kind of study this is. And so to summarize these in a few words, you have first a case control study. So in a case control study, you are looking at some particular outcome, let's say lung cancer in the case I gave you, and then you're looking back at the risk factors. So again, you start with an outcome, and then you look back at risk factors retrospectively. Then you have a cross-sectional study, and that looks at a certain point in time and assesses the prevalence of some kind of disease or some kind of outcome in a population. And then lastly, you have cohort study, and this is a type of long-term study or some kind of study over time where you're looking at a certain cohort, which is a group of people that share some defining experience or characteristic, and you are following them over time and looking to see, what's happening to them, or what risk factors they have, what diseases they have due to some shared characteristic. All right, these next 4 studies I'm going to hit pretty quick because they're not as important, but I think it's still good to know. So the first type of study is called a single blind study. And so in a single blind study, you have patients who are either the part of the control group or the experimental group, and they're given some medication, let's say, again, a vaccine. And so the patients are blinded in a single blind. In other words, patients do not know if they're receiving the placebo, which is the control, or they're receiving the vaccine. However, the person who is administering this vaccine does know who's getting what group or who's getting what treatment. However, in a double-blind study, the patients are blinded, i.e., they don't know if they're receiving the treatment or the placebo, and also the physician is being blinded. So the physician doesn't know if they are giving a patient the vaccine or they don't know if they're giving the patient a placebo. And so this controls for some of the intrinsic biases a doctor may have. Say that he or she knows which patients are receiving the treatment, so then they expect these patients to get better. And then without even knowing it, they might be treating those patients a little bit differently. And so a double-blind study controls for the effects seen in researcher bias. Another type of study that may come up is called a randomized controlled trial, or an RTC. And so a randomized controlled trial is a type of scientific, often medical experiment, which aims to reduce bias when testing a new treatment. And so people participating in this trial are randomly allocated to either the group receiving the treatment, again, let's say it's a vaccine, or the group receiving the placebo. And so that group, again, is the control. And so this randomization minimizes selection bias, which I'm going to get to later. And in a RTC, the physicians and the patients are blinded. So it's a double-blind trial. And so these are considered the gold standard for a clinical trial. The next type of study I'm going to talk about is called a dichotic listening task. So a dichotic listening task is a psychological test commonly used to investigate selective attention within the auditory system. And I'm going to show you how this works, kind of first person. So if you don't have headphones on right now, this is going to sound like shit. But if you do have headphones, make sure that both are in your head at the same time. So what I want you to do is listen to your right ear and do what I say. Again, this is your right ear. Listen to what's going in the right ear. Take 5, 3, 7, and multiply it by 37. Now subtract 2, 41, and add 4 to that number, 89. Now divide this 13. Number by 2. Now what I want you to do is tell me which famous Denver Broncos football player wore the number that you just calculated. If you don't know this number, then obviously you need to work on your math skills. So the answer was number 7, which is John Elway, great football player. Anyways, the point of this was to show you that what researchers will do is they'll put 2 different things in your ear. They'll pump, a song into one ear and then in the other ear math, and they'll say, okay, you're able to pay attention to one thing in one ear, but whatever's playing in the other ear, you just completely don't even think about, don't even listen to. And so if you picked up on what was special about the other numbers I was saying into your left ear, then you're pretty good. But if not, and if you didn't realize what I was telling you in the left ear were, I was naming off a bunch of prime numbers. And so if you go back, you can hear in your left ear a bunch of prime numbers. But you are a lot less likely to pick up on that because of selective attention. All right, so that is it for the study types. If you want more examples and cool real-life examples, I really recommend a podcast called the Best Science Medicine Podcast. Basically, there are 2 to 4 Canadian doctors that talk about recently published clinical data and use a lot of terms that I just used. And if you're able to understand what they're talking about in terms of, they'll use a lot of they'll say the odds ratio is this, and this was a RTC that had 50 patients, and this isn't enough to be statistically significant. And so they'll get into stats, they'll get into a lot of good stuff that I think is good for the MCAT. So if you can understand them, you will definitely understand the MCAT. The last topic I want to cover here in this podcast is research limitations and study bias. There will definitely be a few questions on the MCAT that deal with study limitations. They really like to test that. So you need to be able to recognize shortcomings within studies that are presented in the passage. And this is kind of a very broad topic and somewhat common sense. So what I'm going to say about this is practice lots of passages. You will get used to recognizing limitations if you do this. And when you read the passage, try to read it as though you're critiquing the study. Try to point out where the study falls short and where it has strong points. And some of this will have to do with bias that is introduced within the study. And so I'm going to go through different types of bias, and hopefully that will give you an idea of how studies can have shortcomings. And again, keep in mind that this is a really important topic for the MCAT, so really pay attention, make sure you know these different types of bias. And this is going to be a bunch of terms, bunch of definitions, and again, I'll give you examples that will hopefully help you kind of remember in your head what these different types of bias are and mean. So it's important to note here that the types of bias I'm talking about in this case are experimental bias. I'll get into cognitive biases later in another podcast. All right, so the first type of bias I'm going to talk about is called confirmation bias. And so in confirmation bias, people seek out only facts that confirm their current beliefs. So say a researcher has a theory that cells are not round, and he believes in fact they're flat. So he looks through a bunch of old research papers and finally comes across one research paper out of 1,000 that says cells are flat and describes why they're flat and, backs it up with whatever bullshit evidence it has. Well, now that researcher gets all pumped up and he goes and he exclaims, "I knew it. It has to be true," even though he just read through 1,000 other papers that said cells are actually round. So again, that's confirmation bias. The next type of bias is called social desirability bias. And so this is a type of response bias that is the tendency for survey respondents to answer questions in a manner that will be viewed favorably by others. So election polling is a great example of this. And so you can think about a candidate who is not necessarily the most attractive candidate to say that you support. And so what happens is people are polled and said, okay, are you going to vote for candidate X? And, maybe the public perception is that that person is bad or that person is negative. And so people are more likely to respond and say, no, I'm not going to vote for this candidate because they believe that their response essentially won't be judged by the person giving them this questionnaire. And this is one of the reasons why polling data in terms of elections is not always very accurate. The next type of bias I'm going to talk about is called researcher bias. And so this is when researchers influence the results of a study in order to portray a certain outcome. And this can be done by researchers without them even realizing that they are biasing the results of an experiment. This can be as simple as a researcher treating one group of participants of some experiment differently than the other. And this is what a double-blind study helps control for, right? Because if this researcher doesn't know who's receiving the treatment, then you know that they're not going to have some kind of bias where they unknowingly treat a group of patients better than the other. A classic example of researcher bias comes from the case of the work done by Cyril Burt, who was a psychologist best known for his work on the heritability of IQ. He thought that children from families with low socioeconomic status, i.e. people in the working class, were more likely to have lower IQs compared to children from higher socioeconomic statuses. And his scientific approach to intelligence testing was quote unquote revolutionary by his own perception, and essentially said that he proved that children from the working class were in general less intelligent than those in the upper class. And this led to the creation of a two-tier educational system in England in the 1960s, which sent middle and upper class children to elite schools and working class children to less desirable schools. Later on, though, Bert's research was debunked, and a lot of people concluded that a lot of his data was actually falsified. And it's now accepted that intelligence is not completely hereditary. And so, in this case, you could see that the researcher biased his results. Of course, this was not on accident. He actually falsified data, but again, that falls under the category of researcher bias. The next type of bias is called observation bias, which is also known as the Hawthorne effect. And this is when the behavior of a study subject changes because they recognize they're being studied. So say, for example, a researcher is trying to assess child violence. So they do an experiment where they put two children in a room with only one Xbox and one controller. They hypothesize that the children will fight over who gets to use the Xbox controller and that some kind of physical altercation will occur. However, when the children are placed in this room together, they start to act differently because they know they're being watched and no violence occurs. So the researcher then concludes that, okay, these children are not intrinsically violent. This is obviously a bunch of malarkey. It can't be concluded. This conclusion can't be made because there was some observation bias. The next type of bias I want to talk about is called detection bias. And this is when there appears to be an increasing trend that is caused by some factor being investigated, but instead is caused by an increase in detection of whatever you're using to measure your data. So let me give you a quick example. So think about cancer. Let's say you're looking at a specific type of cancer, prostate cancer, for example. If you're looking to see, okay, how have the rates of this cancer changed since the 1900s, and you compare that to the rates of prostate cancer now, you'll see that there's like a crazy increase in the number of cases. Well, is this because cancer has increased by a lot? The rates of cancer have actually increased? Or is this just because we've got better at detecting cancer? Well, it's more the latter. We've more been able to better detect cancer. That's not to say that cancer rates haven't increased, but the data would suggest that cancer rates have increased, exponentially or just by a ton, and that's just not the case. And more has to do with the fact that we have better instruments now. We can detect cancer earlier, and that is known as detection bias. The next type of bias that I'm going to talk about is called selection bias, and this is when subjects used for a study are not representative of the target population. Here's a very marked example that happens in real life. Say you want to study a new heart disease medication. So you choose a RTC that's double-blinded, but let's say that you don't include any women in your study. Well, women get heart disease too, and it's somewhat difficult to extrapolate data from men to women. There's biological differences between men and women that account for that. But if you don't have women in your study, then it's harder to say, okay, well, this is the dosage that they need to take, and this is how it affects them. So women are usually included in studies in order to then extrapolate this medicine out to the whole population, right? Which includes women, I would hope. So again, selection bias is when the subjects used for your study do not represent the whole target population. The next bias is called subjective bias or subject validation. And this is when, in questioning, a subject will tend to consider a statement correct if it has personal significance to them. So let's say that you are shopping for new shoes online, and one of the reviews to these shoes say that they're great for powerlifters. And say you're a powerlifter. Well, now you are more likely to buy these shoes because they have personal significance to you. Let's not even say that, let's say they're not even lifting shoes, or they're not made for powerlifting, but for whatever reason, someone says, man, I'm a powerlifter, these shoes are great. Well, if you read that and you're like, oh, damn, I'm a powerlifter too, that's sweet. And they say these shoes are great, maybe I would love these shoes. So that's subjective bias when a subject tends to consider a statement correct if it has some kind of personal significance to them. And last but not least, we have attrition bias. And attrition bias occurs when people drop out of a long-term study. And so, as I'm sure you could put together, when you lose people from a study, you're losing data points that could alter the average of the data, especially if you have a small sample size. Let's say that you have a sample of 5 people, and now you lose one of those people. Well, that's 1 data point out of 5. That's a lot. And so attrition bias can really affect a study. It can bias a study. And so that wraps it up for the Research Design and Study Types podcast. As always, thanks for listening. If you have any comments or concerns, please email me. Hope you listen to the next one. All right, now for the segment I call the Mcat Advice of the Day. So today I have a quick bit of advice for you, and it has to do with math, and that is round your numbers. When you're doing calculations on the Mcat, you don't have a calculator, and you don't want to spend all your time doing these calculations. If you have something like 5.89, round that shit up to 6, and then do the calculations with 6. It's going to save you some time, and a lot of times the answers are far enough apart where you can say, okay, I know it's close to this. All right, I'll pick whatever is closest to that number. And think about, a lot of times I'll give you constants like avocado's number, which is 6.022 times 10 to the 23rd. Again, round that off to 6 times 10 to the 23rd. So I think this is just a small little strategy that helps a lot. Round, save yourself time on the Mcat. Hey, what are you doing? Hey. Sam's Mcat Basics is written, produced, and recorded by Murph the Dog. Special thanks to Murph the Dog for this episode.
Each episode of Mcat Basics is brought to you by Med School Coach. To access Med School Coach services, including Mcat tutoring and medical school admissions advising, visit our website at medschoolcoach.com. Good luck as you prepare for the Mcat, and we hope you tune in again next time.